Today I'm here at the Quantum Nano Center in the University of Waterloo in Canada. The Quantum Nano Center is the home of the Institute of Quantum Computing, which is one of the greatest research hubs in quantum computing in the world, with over 300 researchers across 30 different research groups working on some of the hardest challenges in physics, chemistry, and engineering, from developing new quantum algorithms to researching new quantum materials. The Institute for Quantum Computing is also one of the greatest proponents of quantum education in the world, as it prepares the students of today to join the quantum workforce of tomorrow. Today I'll be joined by Dr. John Donohue, who's the Senior Scientific Outreach Manager here at the Institute for Quantum Computing. After obtaining his PhD at the University of Waterloo in Physics and Quantum Information, John went on to do his postdoctorate at Paderborn University in Germany in nonlinear quantum optics. After returning to the Institute for Quantum Computing, John has been responsible for delivering lecture content to the general public, to undergraduate students and to graduate students, as well as for developing the quantum curriculum of today and tomorrow. Welcome back to Quantum Walk Wednesdays by QSYS, and I hope you enjoyed today's episode. Welcome, John.
Hey, thank you so much for having me.
It's nice to meet you.
You as well.
Yeah. So for a lot of our viewers, this would be the first time that they may have heard of quantum computing, or if they've heard about it before, it might have been just as a buzzword. How would you briefly explain what quantum computing is to someone who's new to this field?
Yeah, so essentially the big idea of quantum computing is really just taking ideas that we've had about computing and changing how we're building these things. So think about what a computer is. Well, for a lot of people, a computer is kind of a magic box that we enter information and we get solutions to problems out. But what's going on inside that computer is something physical. We have the state of some transistors that are changing, and if we understand the rules of electrodynamics, Maxwell's equations, we can understand exactly what's going on in that computer physically. Now, what happens if we change the rules of physics for these devices? So what about if instead of something that obeys the rules of classical mechanics, electrodynamics, for example, we replace those bits with something that needs the rules of quantum mechanics to describe it? Thinking about individual atoms, thinking about individual photons, thinking about macroscopic quantum states and quantum circuits, for example. So all of these kinds of things cannot be described by classical mechanics. We need the rules of quantum mechanics. And, it's not too much of a logical leap to say that we might be able to solve some problems that take explicit advantage of the fact that these obey a larger set of rules of physics. Now, of course, going from that kind of hand-wavy explanation to how do we actually dive down into this, how do we actually build these algorithms, is a whole field in itself. How do we take advantage of properties like entanglement, like superposition, to solve certain problems more efficiently? That's kind of the field of quantum algorithms right there in a nutshell. But that's kind of the big idea, is how do we use quantum systems to solve problems more effectively?
That's a very interesting explanation. How would you say that the Institute for Quantum Computing, what role does it play in that, in quantum research and quantum education?
Absolutely. So the IQC, we've been around at the University of Waterloo since 2002, so we're over 22 years old at this point. IQC, we'll look back at what was going on in 2002. This was only 5 years after Shor's algorithm was proposed for factoring numbers using quantum devices, only a couple years after the DiVincenzo criteria were established for what's needed to actually build a quantum computer. So we're talking the pretty early days of quantum computing. And what was kind of known at that time was, in the world of quantum computing, we had a whole bunch of people who are kind of interested in it from the math and algorithm side, and a whole bunch of people on the experimental side who were just hearing that this was a bit of an idea and starting to work on some fundamental experiments here. And if we really wanted to push this field forward, what would be important is that we're bringing together people with those kind of expertises into the same room. So IQC was really founded on how do we get people who are from math, from computer science, from chemistry, from physics, from engineering, who in principle all work with the same ideas, but speak entirely different languages, together into one building, working together to help advance this field as one, establish that common language, establish that community, and really build quantum information as a multidisciplinary field. So that's kind of the ethos of IQC for the past 22 years. We've grown to over 30 independent research groups, 7 different departments at the university, 3 different faculties, and over 200 graduate students at any given time.
That's incredible. Yeah, IQC is probably widely regarded as one of the biggest research institutions in quantum computing, specifically in the world, actually. And honestly, that might extend past just IQC itself as well. I've heard tell of an ecosystem that IQC has been trying to develop in this area in Waterloo for a while. It's often referred to as the Quantum Valley. Could you tell me a little bit more about that?
Yeah, so that Quantum Valley idea really goes to kind of Waterloo as a whole. So Waterloo has invested heavily in quantum technologies over the past 20 years, IQC being a big example of it, but we also have heavy investments in fundamental physics with institutes like the Perimeter Institute. We have a variety of startups and companies who work here on quantum technologies, open resources like the Quantum Nanofabrication and Characterization Facility to help accelerate this research both at the academic and industrial level, as well as, let's say, funding agencies like Quantum Valley Investments. So these institutes and these partners kind of all work together to help establish quantum technologies in the region through a variety of mechanisms, through academia, through training students, through providing industry opportunities, providing industry funding, providing networking opportunities, essentially trying to find ways to make everyone work together to help quantum computing and quantum information technologies as a whole scale up.
Thank you for telling us about the educational opportunities that's available at IQC. I wanted to go back to a point that you mentioned earlier, which was about how many research groups that there are present here at the IQC. Would you be able to give us some examples of research that's being done currently at IQC?
Absolutely. So there, as mentioned, we have over 30 research groups. That gives us a wide variety as well as numerous representation among the departments at the university. So we do have many people working on both theory of quantum information as well as experiments in quantum information. So for example, on the theory side, we might have some people working on quantum algorithms research, looking at different modalities and different paradigms. You can actually prove things directly about advantages in quantum circuits. So maybe it's very difficult to say that this algorithm has an advantage for all possible problems, but if you look at a specific subset of problems like shallow quantum circuits, for example, maybe we can start proving things more directly. We might also be looking at ways to characterize existing quantum devices, looking at benchmarking them, looking at the techniques needed to actually determine that, looking at new kinds of error correction protocols, things like that that can really push this field forward. Also we might be looking at other things that are perhaps, let's say, not directly related to quantum computing, but related to other aspects of quantum information science. So quantum information science, we are building quantum computers, but we're also looking at quantum communication, we're looking at quantum sensing, we're looking at building quantum materials. So on the theory side, we might have people looking at how can we build quantum repeater networks and what's needed to actually make that happen. We might have people looking at different security protocols for quantum key distribution and how to make them work in the real world. What is actually going to work when we get rid of all our kind of perfect world idealizations. Yeah, these are some of the research projects that happen in theory at IQC. Now on the experiment side, we do have people working on a variety of different platforms. We should note that we actually spread between many different buildings here, so we have some located right here in the Quantum Nano Center and some others located in the Research Advancement Center, usually divided by experiments that need large magnets in one building, experiments that are afraid of large magnets in the other building. But we do have groups working on, for example, building superconducting circuits out of aluminum, cooling them down to 10 millikelvin, and looking at that for building new kinds of quantum simulators, new kinds of quantum radar technologies, as well as building blocks of future quantum computers. We have people looking at trapping individual atoms and individual ions, using those as quantum simulators, as advanced quantum sensors, to understand molecular chemistry better, and actually working towards building open source quantum computers through one of the startups they founded there, Open Quantum Design. We also have people working in photonics. We have a quantum satellite mission, the Quantum Encryption and Science Satellite, or QSAT, that's housed at the University of Waterloo. So one of the ground stations is actually in the Research Advancement Center building up north. They're looking at building quantum communication between the ground and a low Earth orbit satellite, as well as building a lot of sensors in the photonics range as well. So for example, looking at building very sensitive, very broadband single photon detectors out of nanowire quantum dots fabricated at the Quantum Nanofabrication Characterization Facility right here in this building.
Speaking of which, quantum computing and quantum sensing as an extension has always been something that I think in the popular media has been popularized as something that's super far in the distance.
Yeah.
But with quantum sensing specifically, or even quantum computing nowadays, it's almost seemed like something that's already being achieved, or a lot of applications have been achieved. In which case, I'd like to ask you, what are some developments that you think have already come out of these, these initiatives to explore more of quantum computing or quantum sensing? And why should people be excited about this?
I think people should be excited. I'm I'm a scientist at the end of the day. Why do I think people should be excited? Because we're doing really cool science. Because we're able to do things like trap individual atoms and move them around into different configurations and move towards doing something really cool with that. Because we're able to cool down these circuits down to that 10 millikelvin level and fabricate them with enough precision that they're truly mimicking the behavior of the quantum world. Because we're able to send photons from the ground to space. The fact that we're able to do these things in itself is really cool. The fact that there are applications is honestly kind of secondary to a lot of scientists. But still, we're able to do these cool things and we can use them to build real things. On the quantum computing side, it's a very academic discussion right now. How far until we can actually get a real computational advantage out of these? How far until we can actually get these kind of quantum advantage experiments to be, rigorously proven as a quantum advantage over existing classical techniques. And of course, there's always going to be a little bit of controversy, especially when industry gets involved in terms of, let's just say, how quickly we can move towards making those claims. But that being said, there have been unambiguously strong achievements in the last year. Some really strong achievements in quantum error correction that can be pointed to in neutral atoms that have really pushed that field forward. Some really strong results in photonics on quantum advantage with these boson sampling systems that have shown a path forward for those kinds of systems, as well as some incredible investments in scale-ups in the superconducting circuits area as well as quantum networking via these spin samples. So some really cool academic results that, don't get me wrong, are not saying we have quantum computing today, but are really showing that we're on our way to it, that we're making strong progress. On the sensing side, is a bit more of a diffuse area, let's say. There's, unlike quantum computing where everyone's kind of like fighting towards like, okay, here's a few criteria that we need to satisfy to build this quantum computer. Quantum sensing is more or less something that is looking for solutions constantly and finding them. For the record, once again, MRIs have existed for a long time. We found solutions for quantum sensors, but it's hard to point to like the quantum sensor because such a thing doesn't exist. Different frameworks, different kinds of technologies, different kinds of platforms have different advantages in different areas. But we have seen, for example, a lot of progress in using nitrogen vacancy centers as very sensitive magnetometers. We've seen advances in electron spin resonance techniques for medical applications. So there's ways that we're finding applications of these ideas.
For sure. With regards to specific applications, John, you did your postdoctorate in quantum optics. Could you tell us a little bit more about what you might have worked on at that point?
Yeah, so back when I was a graduate student, I was actually working here at the Institute for Quantum Computing in the lab with Professor Kevin Resch. And what we were doing was looking at building entangled pairs of photons through a process called spontaneous parametric downconversion, essentially splitting blue photons into two red photons. And since they come from the same blue photon, they're entangled with each other. Now, what we were kind of playing around with was looking at different ways to explore their properties in the time-frequency domain. So you might have heard of space position uncertainty before. If I know more about its spatial position, I know less about its momentum, and vice versa. The same applies to the time and frequency of a photon. The more I know about when to expect it, the less I know about its frequency or its color. So we're looking at ways to measure in that domain on a scale that made sense for the photon. So the lasers we were using were femtosecond lasers, so that's 10 to the power minus 15 seconds. So we were looking at measurement techniques that worked on roughly that order of magnitude. We're able to do things like, for example, map out the correlations, map out the entanglement in the time frequency degree of freedom for these photon pairs. So, essentially building ultra-fast measurement techniques and also broader measurement techniques that could look at not just when that photon is or what color that photon is, but actually what kind of time frequency mode it occupies. So kind of the analogy to Hermite Gaussian modes and laser cavities, but applying that to a time frequency degree of freedom and looking at encoding and processing high-dimensional quantum information in those modes. Now, if I sounded like a bit of a madman talking about that, that's normal because that's what happens when you ask people about their research. It's going to sound very esoteric and very directed, and that's kind of the beauty of research, is you get to focus on your weird little problem and really dive all the way into it. But if kind of backing up from that, looking at what we were working on ways to measure photons at the ultra-high, with very fine time resolution, looking at ways to extend things to high-dimensional encodings in photonics, in light, and even though it kind of seemed like we were going down this rabbit hole while I was in the thick of it, if we back up from it, we can really see ways that this kind of interacts with a lot of other photonics research. Now it's relevant to not just kind of the other photonics research that happens at other universities, but the kind of work of companies like Xanadu, for example, that really work on building these photonics infrastructures into real usable devices.
So John, just to reiterate on, this kind of came up in conversation earlier, but as the scientific outreach manager for the Institute for Quantum Computing, what does your day-to-day look like?
Yeah, so essentially we wake up every day and try to find ways for more people to engage with quantum information science. So a lot of times that can be, working with teachers one-on-one, that can be working with them in workshops, that can be setting up workshops for high school students, giving opportunities for our graduate students to teach high school students and other student groups, as well as a lot of development. I'm a big believer in hands-on activities, so we're in the quantum information lab for education and outreach right now, and this is where we actually build a lot of materials for students to engage with quantum mechanics at the introductory level. We also do things like run museum exhibits, we'll do public talks, kind of whatever, anyone who's willing to listen, we'll find a way to talk to quantum about them.
For sure. It's very good that a lot of the initiatives that IQC has been doing, especially that you've been doing in your role, have been so accessible to the general public as well. And I think that's a really good thing.
That's the dream.
I wanted to ask, since you've been involved with this field, or specifically about educating people on quantum for so long, a lot of people have been pushing more recently in how to get quantum more accessible to people, how to get people more educated in quantum computing, how to get people interested. What do you think about the current state of quantum education today?
I think one of the bigger challenges is not so much how do we, get people who are already in their undergraduate degree to move forward with quantum science, but how do we get people there in the first place, especially when we start looking at underrepresented groups. How do we create those opportunities? How do we allow them to see themselves exploring quantum mechanics? And it's one thing that I've seen a lot of, that I'm sure that everyone's seen a lot of, is that we look at, okay, someone took a physics course in grade 11 and got tired of the math about blocks rolling down a plane and kind of gave up on it. So how can we show people that, okay, physics, there is math involved, there's going to be some challenge there, and yes, we do need to understand how a block rolls down a plane. But if we take those steps, we can eventually get to understanding how an atom holds itself together, how to build photons one at a time, and how to use quantum mechanics to solve real problems. That's really cool stuff. That gets students interested. And if we can get that message out to them, hopefully we can build more people who are interested in science, technology, engineering, mathematics, and willing to kind of follow the quantum path all the way to the end.
That's a very interesting hope that you brought up, actually. And I think it's shared a lot by people in this industry. Especially, there's been a lot of institutions nowadays, such as QEra, Xanadu, IBM, that have been more interested in getting educational programs into universities, but beyond that, just generally having more resources accessible to people to sort of build the quantum workforce of tomorrow. What do you think would be the next steps in popularizing, say, an education in quantum computing or quantum technologies, quantum sensing?
I would say for popularizing education in quantum computing, right now we have to always kind of take a little bit of perspective and note that we are still in the early days of quantum computing. And yes, the industry is growing very fast, and we need to make sure that there are people who are interested, who are able to fill those spots. But frankly, what's going to happen to really accelerate that is major applications coming out using quantum computing. We have to kind of look back to classical computing as an example there. Once the applications come out, the people follow. That being said, I think now is a really good time if you want to get people to be involved in quantum computing. Inspire the people who have curiosity to do so. Make sure that they have room to play around. The kind of people who are going to be interested, generally speaking with broad generalizations, but a lot of people who are interested in being on the ground floor of these kind of technologies, they're the people who are the dreamers, they're the people who want to have the imagination, they're people who want to be able to explore. So making sure they have the tools they need. Open source resources are a great example of that. Making sure that they have mentorship, and making sure that they have opportunities, and make sure they're able to see themselves there. Make sure that it's accessible. It's not seen as this weird ivory tower that only people who are solving differential equations in grade 7 can access. It's nothing like that. You can get in there, you can do it. You can play around with quantum mechanics and help build the quantum future. There's work to be done. There's work to do that inspiration. There's work to make sure people can see themselves there. There's work to make sure that word gets out to them. And from a government perspective, there's funding that needs to be done to have that. These people need to have opportunities. That means there need to be these programs. However, I do think that we will see the kinds of people who get interested in this field broaden out as the applications start really coming to fruition. Yeah, but I think right now it's really inspiring that curiosity, inspiring that vision, and inspiring, that room to play around,
for those who are already interested, who already have that curiosity in learning more about quantum computing or about quantum mechanics or just quantum science in general, what would you recommend to students or even professionals or just the general public who wants to learn more about this field and get more involved?
Yeah, so I'd say to get more involved, depends on exactly what way you're coming from. If you like the coding stuff, checking out Xanadu's resources, IBM's resources, there's a wealth of open source material there and a big community there to help support you. If you're the kind of person who learns through coding, that's perfect. If you like more hands-on stuff, highly recommend checking out some of our programs like USEQIP and like QSYS. And we can help you go through and get into some of that material there. And then, if you're studying in university and you're interested in this field, consider a STEM field. It doesn't have to be physics. I'm a physicist. I love physics. But if you're in engineering, if you're in chemistry, if you're in math, and you're in CS, there's ways to get involved and kind of take courses, take research opportunities that can help introduce you to the field there as well. And that's both here at the University of Waterloo, as well as at many universities across Canada and around the world.
Awesome. So thank you so much, John, for all the advice that you've given and our talk today. As we finish off this interview, is there anything that you'd like to promote in particular, or any research initiatives, or just initiatives in general that you're very excited about?
Hey, follow IQC on LinkedIn, follow us on YouTube, and we'll be posting things there. Follow our outreach page if you're interested on the education side, if you're looking for workshops for your classes, for any high school teachers listening, for example. Just keep an eye on the world.
Okay, awesome. Thank you so much, John.
My pleasure.
Nice speaking with you.
You as well.
Thank you so much for watching today's episode of Quantum Walk Wednesdays. We hope you really enjoyed. Make sure to check us out on Instagram, YouTube, and TikTok. And make sure to check out our conference happening this September in Toronto and Vancouver. That is the QSYS conference. Make sure to check us out. Bye.